You are given an array, and in one operation, you can pick any triplet. Suppose they are L, R, and M. And if this condition is satisfied, that is, the maximum value amongst these three integers is equal to the middle element, then you are allowed to delete either the left element, you can either delete this element forever from the array, or you can delete the right element. You have an independent choice that you can make. And after this element is deleted, this and this gets closer. So this block is removed completely from the array. So your goal is that given an array, you have to figure out how many operations will you have to do, so that at the end of all the operations there are no such triplet that satisfy this condition, which is at the end of the array, if this is the array final array that is remaining, then I should not be able to find three consecutive numbers such as L, M, and R, such that the maximum of these three numbers is equal to the middle element. So you have to find out the minimum number of operations to achieve this final array. So in this video, we will talk about some techniques to solve this easy looking hard problem. Now, how do you start thinking about it? You can try to apply various strategies, but they might or might not be correct. So in problems like these, which involve doing certain operations, it is usually best to start small and think of some cases that you can be 100% sure that you are handling correctly. So how do we do that? So first of all, notice that in one operation, you are deleting exactly one element. So this means if you have to minimize the number of operations, it means you have to minimize the number of deletions. This also means that you have to maximize the number of elements that you retain at the end. So this is one observation. This is not really an observation, just a transformation of this statement. So maximize the number of elements at the end. So this is one interesting observation. Now the second observation you can notice that every time this condition is satisfied, that is max of left, right and middle is equal to middle, then you can see that only the left is deleted or the right is deleted. The middle is actually not deleted. This means that the maximum element in one operation is not deleted. So this immediately gives us a hint that you should start your investigation by looking at the maximum element of the array. So let's take an example, and suppose you have this array and you can already see that there are a lot of pairs that satisfy the condition. For example, if you consider this pair 6 9 3, this is a triplet where the maximum element is in between. So of course you have to either remove 6 or 3 or both of them in two operations. Now let's start our investigation by looking at the maximum element. You know that if this is the maximum element, then every time it participates, it can either participate as a left element or a right element or a middle element. So if it participates as a middle element, so if this is actually a middle, and anything that is coming from the left side and from the right side, their maximum will always land here. So this element anyway cannot be deleted, because when it acts as a middle element, only the left and right gets deleted. So let us consider the case when this maximum ends up acting as the left element. So if this is acting as a left element, then somewhere on this right hand side we should have a middle element and we should have a right element. But you can see that no matter what triplet that you produce, the maximum of this triplet will always land on L. It will never land on M. Why? Because 9 is the maximum for the entire array. Similarly, now consider the case where this 9 acts as the right element for the triplet. So the left element must come from the left side and the middle element must come from the left side. Then you can see that no matter what, the maximum of this entire triplet will never fall on the middle element. It will always fall on the right element, because 9 is the maximum element of the entire array. So this means that 9 can never be part of a triplet that satisfies this condition. And even if it is part of this triplet, then you can never delete 9. I mean, 9 definitely can be a part of a triplet. For example, if you have L over here, if you have M as this and R over here, so 9 is definitely a part of a triplet where the maximum lands in between, but it can never be a part of a triplet which can delete 9 from the array. So the first observation or the second observation that you can make is the maximum element of the array, maximum will remain till the end. This is a very clear observation that you can make, and you can prove this using the arguments that we just did, that this observation is actually correct. So now let's follow this line of reasoning and see where it leads us. So if you are not allowed to delete 9, so this means that this 9 will be present in the array for sure. But you have to keep in mind that the final result should not contain any triplet that satisfies this condition. And we already talked about the case where 9 can satisfy this condition as a middle element. If you take some element from the left hand side, you take some element from here, and then you take some element from here. So we have to avoid that case altogether, so that this 9 does not become as a middle element. So one thing is clear, either this entire left subarray is going to get deleted, or the entire right subarray is going to delete it. So that is the second observation that we can note. Left or either left or right subarray of the maxima will be deleted. So we have our observation over here. Now, how do you decide which subarray to delete and which ones to keep? Remember that your goal is to maximize the number of elements. So let's continue our chain of thoughts and see where it leads us. So once you know that 9 will be for sure in the final list of elements, and you know that only, so what we'll do is 9 has a left subarray and it has a right subarray. So let's create a node out of this 9 and then add it as a left subtree. And we'll talk about how to actually represent this subtree, but for now just assume that this is a node in some tree that will describe what exactly that is, and then there is a tree on the right hand side for the right subarray. And you know that only one of these subtrees will remain till the end. The entire thing will have to be deleted. So that's fine. Now let's focus our attention on the right hand side. So once 9 is guaranteed to be in the array, you can notice that we still have to solve that same problem in this subarray, in the subarray created from the right hand side. Why? Because this entire subarray will go on the right hand side, and let's look at the maxima in the right hand side of this 9. So what is the maxima? The maxima is 8. So you can see that once 9 is out of the picture, because 9 is guaranteed to be in the final result, nobody is capable of deleting 8, at least from this segment. Why? Because whenever whenever 8 participates, it will either participate as a middle element, in which case nobody can delete it because you are only allowed to delete the left and right element, or it participates as a left element or a right element. But if it does that, then the middle element cannot be the maxima. Why? Because you cannot cross the boundary. You cannot cross this boundary, because we know that 9 will for sure exist. So nobody can delete this 9. So that is why this 9 creates a virtual boundary in between. So this gives us some hint that after selecting the maximum element, everything that remains to the right, you have to select the maximum out of it. And then you can apply the same logic that everything that remains to the left, you have to select the maximum out of it. So let's make a tree. And right now we are not even sure like why are we doing this transformation and what exactly will we do that tree. But let's explore this approach, see where it leads us. So let's attach 8 because that is the maximum element on the right hand side. And on the left hand side, what is the maximum element? That is 3. That is 6. And then at 6, you partition it again. So the left half is 2 and the right half is empty. So you create this 2. Now when you partition it at 8, so when you partition it at 8, you can see that 9 already acts as a boundary, and now 8 is also acting as a boundary. So it creates this left subarray and it creates this right subarray. So the maximum element from the left hand side will become the left child for 8, which is 7. And the maximum element from the right hand side will become the right child for the 8, which is 4. And then if you continue your reasoning, you see that you create 1 as the right child. And for 7, for this subarray, you can see that the 5 is the maximum element on the right hand side, and then 3 is the maximum element on the left hand side. So let's create this tree and this. So we are not even sure why we created this tree, but maybe this tree might help us solve this problem quicker. Maybe we still have to think like what exactly is happening with this tree. So the tree that we have just created, this structure is known as a Cartesian tree. And in the next slide, we'll talk more about Cartesian tree. But right now, you can see that Cartesian tree, this was motivated from this problem statement, because the problem statement was begging for us to look at the maximum element and then look at the second maximum element on the right hand side and on the left hand side. So we got some intuition that we have to create some sort of trees. Now whether or not it's easy to solve this problem on this tree versus this, that is yet to be seen, because technically we have not done anything. We have just represented this array as a tree, and it can actually be, so this is actually a bijection. So you can represent an array as a Cartesian tree, and then a Cartesian tree can also be represented as a permutation. And in the problem statement, they have mentioned that all the array elements are unique. So now let's talk a bit about Cartesian trees before we come back to the problem, and you will see how Cartesian tree makes this absolutely difficult problem trivial. So we'll see. So this is the Cartesian tree. So the rules of Cartesian trees, rules of creation of Cartesian trees are very simple. You start with the entire array and you pick the maximum element, you make it as the root, and then you recursively create the Cartesian tree from the left subarray as the left child, as the left subtree, and you recursively create the Cartesian tree for the right subtree from the right subarray. So you pick the maximum element, you add it over here. Then from the left subtree, you pick the maximum element, you add it as the left child. And then for the maximum element on the left side, which is 2, you add it over here. Then for the right subtree, you pick the maximum element, you add it as the root. And then it splits into 2 halves, just like we discussed. So for each half, you pick the maximum element, 4 and 1. and the left half, the maximum element is 7, and then it splits it again into two halves, 3 and 5. So you add it as 3 and 5. So this is it. This is the entire Cartesian tree theory that you need to know. Now, one important observation that you can notice is that, sure, using recursion, you can create a Cartesian tree from a given permutation. But given this Cartesian tree, can you create this permutation back? So can you think about some approach to do this? So you will notice that two is the first element in this permutation. So how can we arrive at 2? So you can see that this is 9, this is 6 and 2. So you are going to the left and then going to the left, and you are going to the leaf vertex, and then you are printing 2, and then you are going up and then you are printing 6, and then going here, there is nothing, you come back, and then you go here, you don't print 9, or do you? Yeah, you do print 9, and then you go to the right, but you don't print 8. So this means, if you have learnt about this in order traversal, then the permutation that you see on the screen is nothing but the in order traversal of the Cartesian tree that was created. Because because the in order traversal looks something like this. You do something like recurse on the left subtree, then you print the root, print the node value, and then you recurse on the right subtree. This means that the left subtree will be the entire left subtree will be printed first, and it actually makes sense because the entire left subtree is the left subarray, and then the entire right subtree will be printed last, which is the right subarray, and then the node, which is the root, will be printed in middle, which is exactly what it is. So you can do some exercise on your copy, and you will see that this, if you do an in order traversal of this tree, you will get this permutation. So this is just some fact to be known. Like in this problem, you don't really need this fact that the in order traversal gives you the permutation, but at least you can conclude that every permutation has a unique Cartesian tree, and every Cartesian tree has a unique permutation associated with it. So that is why this concept might be useful for you in solving problems related to Cartesian tree, because any permutation or any set of unique integers can definitely be viewed as a Cartesian tree. Now, another important properties of Cartesian trees that you will notice is that they are a max heap. Why max heap? Because the maximum element is the root, and then there is the left subtree and the right subtree, and the both of these subtrees follow the same identical properties. That is, the root will always be the maximum element from the left subtree and from the right subtree. And you can see why that is obvious, because by design of the Cartesian tree, we have already said that the root that you pick, that will have to be the maximum, and then on the left side, the root of the left child will be the maximum from the remaining part, and the root of the right child will be the maximum element from the remaining part. So this is also one trivia, not that it is going to help us solve this problem. Now let's move on to the final part of this video, that is, if given this permutation, and you know that this permutation can now be viewed as a Cartesian tree. Now let's look at what our operations look like on this Cartesian tree. So we said that nobody can delete 9, and then either left half have to be deleted or the right half needs to be deleted, depending upon which one gives us more benefit. So what does this looks in terms of tree? You can see that since 9 cannot be a middle element, right? Because then if 9 is a middle element and there is L and then there is R, then it starts satisfying the property that the maximum is in the middle. So either the left half is going to get deleted, either this entire subtree is going to get deleted, or this entire subtree is going to get deleted. Now what about 8? The same logic follows. Either this left subtree is going to get deleted, or this right subtree is going to get deleted. Meaning you can conclude that no node will have two children. No node will have two children. Why? Because Cartesian tree is a max heap. So if this is a node X and it has two children, let's say L and let's say R, then of course the property is still satisfied, because the maximum of L, R and X will of course be X, and the problem told you to keep on deleting until there is no triplet that satisfies this condition. So one thing you can be sure, that no node in this Cartesian tree will have two children. This means that at each step you have to take a decision. At each step you have to take a decision whether you want to go towards the left part or the right part. So when you start with 9, you can either go here or go here, and then from 8 you can either go here, and then from 7 you can either go here. So you will realize that starting from the root element, you can either go here or here or here or here, etc, etc. You can keep going, and all the elements that you visit on your journey are the ones that are retained till the end, and the remaining are deleted. So your goal would be to maximize the number of elements that are retained. So this means this problem is nothing but finding out the maximum depth of the Cartesian tree. Like, what is the farthest leaf that you can achieve in this Cartesian tree? That is the number of elements that you can retain till the end. So if this Cartesian tree had a structure like so, it had this, let's say it had this, it had this. So in this Cartesian tree, you can notice that, of course, this will represent a unique permutation. Now, if I ask you what is the maximum number of elements that you can retain, so you can retain this, 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 and this, and you can delete the rest of them, and then this is the maximum number of elements that you can retain. And you can see that now all the elements that are marked with two red ticks, they will never form a triplet that has the middle element as the maxima. Why? Because the maxima will always be the higher element, right? Like the one with the lower height. So this will be the maxima, then this is the maxima, this is the maxima. And you can see that this is the optimal. Why? If it is not the optimal, it means that there is at least one red tick and you want to retain one child. So if you want to retain one child, then of course you cannot retain both. You can either go here or you can go here, because if you start retaining both of them in this Cartesian tree, then their maxima falls over here, and this is a valid triplet. So that's why you have to either discard this journey altogether or discard this journey altogether. So the answer to this problem is simply n minus max depth of the Cartesian tree of the permutation that is given to you. As simple as that. N minus max depth. And in a tree, how do you find out the maximum depth? That you can simply find out with dp. So how do you do that? dp or dfs, whatever you want to call it. So that is a very simple problem to do. So max, if you want to find out the max depth of this tree that is rooted over here, depth, like let's say depth, or let's say something like max depth, then you can see that find out the max depth of this subtree and the max depth of this subtree, and the max depth of this would be max depth of root would be equal to 1 plus max depth of left child, maximum of max depth of left child, and then max depth of right child. And this will give you the final answer. You can compute the max depth and print the answer as n minus max depth. So now the last part that is remaining is how do you compute this tree? Because if you are how do you create this tree? Because once you create this tree and once you land in the tree territory, you are able to solve it very easily. But how do you compute a tree efficiently from the permutation that is given to you? Now there are some fancy ways using stacks that do it in O of n, but I don't want to discuss those. I want to discuss the very simplest approach that you can take that just follows the definition. So the simplest approach is just to use the range maxima data structure. You simply query the maxima element of the data structure. You simply query the maximum element of this array. You call it as the root. And then you recursively create the tree from the left side. So the pseudocode will be something like this. So let's say you want to create the tree from L comma R, and then you want to return the root as the return value. So let's say you get the IDX as the max of L to R, and then you do root is equal to IDX, and then root dot left, the left child would be you simply recursively create this left child, create, and left would be L2 IDX minus 1, and you attach the right child, root dot right is equal to create IDX plus 1 to R, and then you return root. So this simple algorithm, even though it requires a data structure, but you can use the atcoders library, atcoders segment tree library to get that data structure to find the range maximum value. And with this you can create that tree explicitly and then do the operation. But even if you don't want to create the tree explicitly, you can see that you want to just do some tree DP on this tree. So instead of creating this tree with this root, you can simply do the recursion directly for the max depth. Like if you want to figure out the max depth of this tree, so if you want to do max depth of an array, from L to R, you can simply do the recursion over here. It will be 1 plus max depth of L2 IDX minus 1 comma max depth of I plus 1 to R. So here you will not need to explicitly create the tree, but even if you want to, that's fine. Now I will not be discussing any of the stack based approach, but if you are interested, you can take a look at some blogs on Codeforces. If you want, I can link those in the comment section. But anyway, like stack based approach is not very tricky or difficult to learn for Cartesian tree, but I just wanted to focus on the ideas behind Cartesian tree. And you can see how this problem, which appeared very recently, I think 1 month back in a Codeforces round, is kind of reverse engineers the Cartesian tree, because you can see that this was a Codeforces problem D, but with Cartesian tree, if you knew about Cartesian tree before, it becomes absolutely trivial. But if you don't know about it, I mean, you kind of invented Cartesian tree by yourself, right? Because you had to kind of get that visualization that, okay, the maximum will be retained and then the second maximum will be retained. But yeah, I'm not saying that you will encounter Cartesian tree soon in your competitive programming journey, but at least this helps to keep in mind that for each permutation, there is a bi-directional mapping between Cartesian tree and permutation. So that's all for the video. Thank you.